So thanks very much for the invitation. It's a pleasure to be here virtually, sadly not physically. And the main idea that I want to talk about today is using meteorites to test ideas about the dynamical evolution of our solar system. So not just the local geological evolution of asteroids, but processes and events that may have affected much of the solar system up to and including the formation and evolution of the moon. And the basic motivation for this is that planets may erase evidence of earlier events if they are active worlds. Erosion may take a crater and gradually destroy it over time, whereas asteroids and other relatively geologically inactive bodies, such as the moon, after a certain point only have collisions to deal with. And so if we're interested in mapping out the history of collisions, these sorts of bodies may be comparable and really quite pristine records of the evolution of the solar system. And my work focuses on reconstructing the timing and pressure temperature conditions of those collisions in order to learn about both the local geological histories and wider solar system events. In order to access these records, I use the uranium-lead isotope system and mineral microtextures, respectively. And so far, I've collected many different uranium-lead ages for meteorites and characterized the microtextures of the minerals that we use to obtain those ages in a variety of shocked chondritic meteorites. And my collaborators have been focusing on lunar samples. Ideally, the next stage will be to compare these emerging records, but to do so, we must be confident that we can expect the same outcomes for impacts of a given velocity and size on small versus large parent bodies. So zooming back out to the basics of the uranium-lead system, before we tackle that assumption, let's look at some data. These perhaps complicated looking plots are for data from Chelyabinsk. This is an LL5 shocked ordinary chondritic meteorite that I studied extensively during my PhD. Picking apart these ages and interpreting what they mean is controversial. Chelyabinsk is a useful case study because it preserves three distinct lithologies. It has a so-called light lithology, which is only moderately shocked, as well as a dark lithology, which is shocked up to about S5. The uranium-lead phosphate in Chelyabinsk has been known since it fell, or shortly after it fell, to return two different ages. An ancient age where the data intersect the Concordia and the upper intercept around 4.45 billion years ago, and a relatively geologically recent age, the lower intercept age. Interpreting these ages is really what's caused the drama, because previous work has shown that these two differently shocked lithologies in Chelyabinsk probably formed at the same time in one event, and yet we have these two ages. And people have debated whether or not the lower intercept or the upper intercept age is dating the collision that formed this breccia. So one idea that we had to distinguish between the two proposed ages and get a handle on what uranium-lead ages really tell us is to see if there is any systematic variation in the measured uranium-lead age between the different lithologies. So from this, you can construct two different hypotheses. If the recent lead loss, which drove the formation of the lower intercept age, was related to the formation of the different lithologies, we would expect a correlation between the location of a grain, if it's in the dark or the light lithology, and the degree of lead loss. You would expect dark lithology grains to have reached higher temperatures for longer during that intense shocking, and therefore to have lost more lead. That is, we would observe a macro scale correlation between lead loss and the setting of the phosphates. The alternative interpretation, if the recent lead loss occurred during a relatively minor event and the three lithologies formed a long time ago, is that there should be no such correlation. We may instead expect lead loss to correlate within each lithology with some kind of textural feature which accommodated lead loss, such as a fracture, which could have damaged the phosphate crystal lattice and promoted lead loss more easily. So we went about testing these hypotheses by obtaining secondary ionization mass spectrometry analyses of uranium-lead isotope ratios in the phosphate minerals that host uranium in Chelyabinsk. These gave us spot compositions that we can then tie at a small scale to the individual grain textures. So what you're now looking at, going back to the graphs, is spot data plotted on a Concordia diagram. The light blue markers indicate the center of ellipsoidal errors for each point. I have plotted on previously measured data from earlier studies with brown triangle markers. On the left-hand plot, the data are color-coded by lithology, purple for the dark lithology and orange for the light lithology. On the right-hand plot, the data are color-coded instead by crystal domain type. The light purple are damaged domains, where we've observed in the SEM fractures, cross-cutting, where we put our SIM spots, and red are pristine domains, where there's no visible defects. Below each plot are the graphs of the cumulative distributions of the 207, 235 uranium compositions, which allows us to get a visual sense and then a statistical sense of how similar the different data groups are. There are several key observations to make from these data. The first is that our data find a much wider range of compositions in previous studies, which avoided looking at these fractured domains. This is quite an important finding. And basically, because there's only so much time, but the data reject the first hypothesis that I outlined. There's no macro scale correlation of lithology with phosphate uranium lead ages. There is, in fact, a strong correlation between damage-related microtextures, such as fractures, and the uranium lead isotope composition. Therefore, we can infer that the collision happened a really long time ago, and the lead loss that took place more recently is instead related to some minor event that mobilized lead only from fracture damage domains. Taking all of these data together, we can calculate a best estimate upper intercept age of the major event that reset the uranium lead isotope systematics of chelybinsk up to be about 4,473 million years ago. And meanwhile, that recent lead loss accommodated by fractures happened geologically recently, within error of the modern day, presumably during some late fragmentation event that launched chelybinsk to Earth. And we've been expanding this type of analysis to many other meteorites. So these Concordia plots are all L chondrites that I've been studying recently. And the upper intercept ages, if we extract from those graphs, are now plotted on screen in descending order. And you can begin to unpick aspects of solar system history with this understanding. You can group them by whether or not they're strongly or weakly shocked. And in this context, that means if it's been shocked enough in the sample to the degree that you would expect the uranium lead system to be reset or not. And you find all sorts of interesting features. You find that samples which you would not expect uranium lead systems to be reset are fully consistent with just normal cooling of an asteroid as radiogenic decay slows down. So on this plot here, all the weakly shocked samples in the top half don't go beneath that red line, which is where the models of radiogenic metamorphism say the uranium lead system should close in asteroids. But the strongly shocked samples have a much wider range and broadly fall in early solar system history and a more recent epoch between about 4.4 and 4.48 GA. That's really interesting, actually, because this is what was predicted in studies of or models of moon formation, which suggests that debris scattered during the giant impact would produce a huge spike in collision ages around 4.45 to 4.48 GA in chondrites. And that's what we're seeing here. So that's a tentative conclusion, but certainly an interesting one. We also see no evidence for the late heavy bombardment. None of these upper intercept ages have been reset between 4 and 3.5 GA. So that may also be consistent with emerging evidence from the lunar record. And this is just to show that it doesn't really matter how you group these strongly and weakly shocked samples. If you split them by their metamorphic grade or petrologic type, you find that the strongly shocked samples are identical to each other. The weakly shocked samples are identical to each other, but are very different from one another. So this is a robust conclusion about the processes that are being recorded by relatively pristine versus highly shocked samples. And if we then look at the lower intercept ages, you find that most L chondrites record an event that happened around 480 million years ago. If you split them by shock stage, as in the previous plot, you find there's no difference, which again just reinforces this conclusion that low intercept ages are not really recording major collisions. They're probably recording fragmentation events, much lower temperatures, and lead loss accommodated by pre-existing damage domains. That's exactly what's been observed in the study of lunar samples, which also record lower intercept ages around this time. And we can be extremely confident that these ages are meaningful because there are terrestrial sediments on Earth, which are absolutely full of fossil L chondrite meteorites, which have been dated exactly to this time, around 475 million years ago. So something happened in the asteroid belt at this time. At least the L chondrite parent body was affected, scattering material towards Earth and quite probably the moon. And future dating work focusing in on craters of that time may well show a spike. And this is another statistical comparison of the distribution width, which just shows strongly and weakly shock samples are completely identical. This is kind of what we've mapped out for the history of the alchondrite parent body, with early collisions and radiogenic cooling, followed up by resetting of the uranium-lead system in relatively late collisions, quiescence until around 470 million years ago, at which point the alchondrite family formed after some kind of breakup event. And to now move on to textures with my last few minutes. The uranium-lead system does seem to be showing similar stories and features in lunar and chondritic samples, but we want to know if the textures show the same. I haven't really shown any textures yet, but I'm going to finish off with some. And merylite, rather than apatite, is the key mineral. Apatite is what hosts most of the uranium in chondrites and in lunar samples, but merylite has many of the more interesting textural features. So here's some examples. In the center of the image here, which is a cathodoluminescence image, you have a grain of intergrown apatite and merylite. Apatite is the complex-looking grain with these fractures going through it, and merylite is the boring-looking grain on the lower right-hand side of the center. This is in Chelyabinsk in the S4.
Can you please wrap it up?
Oh, okay. I'll wrap it up. Okay. Basically, you can find, depending on the shock stage, these recrystallized textures versus really boring textures. And in lunar samples, I'll just skip to the end. I'm running out of time. In lunar samples, you find recrystallized textures really early. So although it's extremely early days, there does seem to be a systematic offset between when recrystallized textures appear in chondrites versus lunar samples. And this is really the next frontier that we need to add into our dating work to contextualize it with how the minerals themselves are responding. Sorry, I ran out of time. Thanks very much.